building off of the last video where we were looking at all of the formulas for derivatives of exponential, logarithmic, and hyperbolic and inverse hyperbolic functions, so let's just work through some derivative examples. And then in the next video, we'll do some integral examples. So these are kind of review from Calculus 1, but also a little bit maybe beyond and including lots of different techniques from our Calc 1 with the derivatives. But a nice little warm up getting us ready for integration of these types of functions. So let's zoom in on this first one. So for all of these, we're just going to be finding the derivatives using our formulas. Now I'm not going to project the reference sheet again, but hopefully you've gotten that filled out. And now we're going to be ready to just jump in and start taking derivatives. So on this first one, we're going to go through this term by term, applying our derivative rules. So the derivative of 5e to the x is 5e to the x, just exponential function. This 3x to the fourth, that we're going to just use our power rule. So that's 12x to the third. Then we have 5e to the x. Now 5e to the x is an exponential function, but it's a base other than e to the x. So the derivative formula here, it's going to be 5 to the x times the natural log of 5. Then we're taking the derivative of the natural log of x. That's going to be 1 over x. Now we have x to the e. Now let's remember that e is just a constant, so that's just x to a power. So this is going to be ex to the e minus 1, just applying the power rule again. Then we've got the common log of 10. Now the common log of 10, when there's no base written right here, remember that there is an implied base 10. This is the common log, the notation for the common log. So since this is the common log instead of the natural log, when we take the derivative, we're going to get, it was a minus, sorry, almost said plus, minus 1 over x times the natural log of the base, so the natural log of 10. And then notice on this last one, we've got pi squared. Well, that's just a constant. So when we take the derivative of that, that's technically just 0, but I'm not even going to write it. And that is my derivative. So there's my first derivative. Now, just remember, we went through that just term by term. There was no products or quotients, just a review of all those basic rules. So let's take a look at another one. Let's take a look at this one. So this one's got a hyperbolic function in it, the hyperbolic cosine, or cosh, and we have x raised to a function. So this is, you know, what we're thinking about here, let's do a little thought bubble. What we're thinking about here is that this has a variable base and a variable power. So it is neither an exponential function, nor is it a power function. It's not x raised to a constant. It's not like x to a number. And it's also not a number to the x, right? This would be exponential and this would be a power function. And we have rules for dealing with those. We just reviewed those on the last example. But it is neither one of those two things. This is actually a function raised to a function where both the base, x, is variable and the power, the exponent, is variable. And so we actually have to do a little bit of work here. We have to get this into a form that we can use a derivative rule on. And so to do this, we can use a process called logarithmic differentiation. So this is a good review of that process from Calc 1. So when we see something like that, we can introduce a log. The gist of logarithmic differentiation is that we introduce a log. So I'm not going to go through and lecture on that process. I'll just remind you of it as I go through the example. So we'll introduce a log. So we'll take the natural log of both sides. So we've got y equals x to the hyperbolic cosine, and we will introduce a logarithm to both sides. Now the reason that we do that is because we have our rules of logs, and our rules of logs allow us to bring this exponent down to the front. So we have the natural log of y equals the hyperbolic cosine times the natural log of x. And now this is in a form rather than a variable base and variable exponent. Now we have a product of two functions on the right side. Now on the left side, we do have a natural log of y. So when I take this derivative, I actually have to take the derivative implicitly. So I take the derivative of both sides of this equation now, because it's no longer just y. Over on this side, we get 1 over y times the derivative of y, which is dy dx. And then on this side, we have to apply the product rule. So applying the product rule, we take the derivative of the hyperbolic cosine, which is sinh, or hyperbolic sine, times the natural log of x, plus, and then the derivative of the natural log of x is 1 over x times the hyperbolic cosine. So we applied product rule, because it was definitely a product on that right side. And then on the left side, we used our implicit differentiation. And now we just have to solve for the derivative. So to solve for the derivative here, I'm simply going to multiply both sides by y, and my derivative of this function, dy dx, or if we like y prime better, we could replace that with y prime, is equal to, now we're going to put our y back in. Remember, y was equal to x, cosh of x, times, now we've got this product, sinh of x times the natural log of x plus cosh of x over x. And that is my derivative using a little process called logarithmic differentiation. And that is a handy tool to introduce a logarithm, and then we have all those abilities to work with logarithmic rules, and hopefully we're pretty comfortable with our logarithmic rules at this point in our mathematical maturity. All right, so let's take a look at another example. I'm trying to get it up on the screen here. There we go. All right, so let's look at this guy. Here we've got the natural log of 3x to the 7th plus 5 all cubed. So, it's kind of funny. In math, sometimes we use these like little shorthand notations that can be a little bit misleading when we think about applying derivative rules, because this is a composition and we're cubing the entire logarithm. So it probably makes more sense, even though it takes more symbols, to write it like this so we can really see the order of the composition. So when we're taking the derivative, we're applying multiple layers of chain rule here. And so when we take this derivative, g prime of x, we're going to take the derivative of the outermost function, the power, so 3 times the natural log of 3x to the 7th plus 5 to the 2nd power. Then we go to the next inner function, which is the logarithm. So the derivative of a logarithm, or the natural log, is 1 over 3 x to the 7th plus 5, 1 over the argument, what we're taking the log of. And then the last layer, the innermost function, is that polynomial. And so the derivative there is 21 x to the 6th. And now we've got the whole derivative. There's not a ton of simplification. I guess I'm going to combine that into one fraction. So we end up with the natural log of 3x to the 7th plus 5 squared times, in the top here we have 63x to the 6th, and that's all over 3x to the 7th plus 5. And there's our derivative. And again, if I prefer not to write the square like that, the little mathematical shorthand, notice I can get rid of the bracket symbol and I could put the square there. But I do think it helps in the beginning to think about that, as we did here with that cube, thinking about, that's the entire logarithm being cubed. All right, let's keep rocking and rolling here. We can get a couple more examples on this video. Let's take a look at this guy. Here, this is the notation here. We got that derivative operator. It's saying take the derivative of the function x plus 1 to the 2x. And this is like the example 2 back, where we thought, oh wait, I've got a variable base and a variable power. So I'm thinking to myself, I need to use log differentiation. So I'm going to come in here, I'm going to say, okay, I'm going to introduce, because this was kind of given to us in slightly different notation. So I'm going to introduce the y here, let y equal x plus 1 to the 2x. And then since I'm looking at that and thinking that's not exponential, that's not power rule, that is a function raised to a function. So I need to do something here to get this into a form I can take the derivative, and that's where that handy log comes in. I'm going to introduce a log to both sides, and then the natural log of y equals, that brings that power down, 2x times the natural log of x plus 1. Now I'm going to take the derivative of both sides implicitly, because we now have the natural log of y. The right side, when we're using this logarithmic differentiation, if all we introduce is a log, then on the left side with this natural log of y, we will always get 1 over y times the derivative of y dy dx, or we could write y prime. Then on the right side, we have a product. So again, with the product rule here, so the derivative of 2x is 2 times the natural log of x plus 1 over x plus 1, technically times 1, the derivative of the inside, times 2x. And then we're going to multiply both sides by y to isolate the dy dx. And when I do that, I find that dy dx, or if you prefer prime notation, y prime, is equal to, we put our y back in, y was x plus 1 to the 2x, and we're multiplying that by 2 times the natural log of x plus 1 plus 2x over x plus 1. Now, we could simplify, we could find a common denominator, but I'm not worried about all that simplification. As long as we've got the derivative and we've got it relatively well simplified, we're good. So we've got a derivative we could work with. If we needed the equation of a tangent line, or if we wanted to figure anything out relative to this particular function related to its rates of change, its derivative, we could do that with this function. Okay, we're on 4. I think we can get a couple more in. Let's try to get at least 2 more in here. All right, let's take a look at this guy. We've got f of x equals 3x squared times hyperbolic tangent of x. So we want to take that derivative. This is just good review of our derivatives of our hyperbolic. So we want to take that derivative. So we're going to be applying our product rule here. We've gotten some good practice with the product rule on these examples. So the derivative is going to be 6x times the hyperbolic tangent of x. And then the derivative of the hyperbolic tangent is the hyperbolic secant squared of x times 3x squared. And that's our derivative. We could pull a little common factor out there. I see a 3x that we could pull out, and we could do that, leaving us with 2 hyperbolic tangent of x, plus here we have just an x left, so x times the hyperbolic secant squared of x. All right. That's a nice little derivative simplification there. That one was a quick one. Okay. Let's keep going. Let's take a look at this guy. And on this one, I added in my notes here, prepping for this video, I added this as a little reminder, because this might not be one that we have memorized yet as we're learning our hyperbolic functions, or relearning, re-familiarizing ourselves with our hyperbolic functions. This one has the derivative of the inverse hyperbolic sign. So the derivative of the inverse hyperbolic sign is 1 over the square root of x squared plus 1. So when I'm taking this derivative, I do notice that I've got chain rule because I've got this inner function here. So since I have my inner function, when I'm taking the derivative, y prime or dy dx, whichever notation you prefer, we're going to have that is going to be what we're replacing our x with in the formula. So this becomes 1 over the square root of, we've got 4x cubed squared plus 1, and then applying the chain rule, we take the derivative of the inside, 12x squared. And that simplifies down to 12x squared over the square root of 16x to the 6th plus 1. And there's my derivative for the inverse hyperbolic sign of 4x cubed. All right, let's get one more. Let's see if we can squeeze one more into this video. I could go for days. It's kind of fun to review all of these formulas and practice with them, but I'm going to stop after this example and let you guys try some on the worksheet. So let's go ahead and in the homework, of course, too. Let's take the derivative of the natural log of the hyperbolic secant of 2x. So again, we've got some layers here of composition. We got to think about what's the derivative of the hyperbolic secant, and of course the derivative of the natural log. But the derivative of the natural log, the outermost function in this composition, is going to be 1 over the argument of the logarithm. So that's the hyperbolic secant of 2x. Then we need to take the derivative of the hyperbolic secant. So the derivative of the hyperbolic secant is negative hyperbolic secant of 2x times hyperbolic secant or hyperbolic tangent of 2x. Then I have to multiply by the derivative of the innermost function, which is 2x. So I've got my 2 right there. And notice that we've got some reduction here, and this becomes minus 2 hyperbolic tangent of 2x. And that is my derivative simplified down really nicely. And that's my derivative. Okay, so that was some good practice, some running through some good practice with some derivatives. And again, we're utilizing all those formulas. I will now here at the end of the video. Hopefully you already have these up in your notes and have filled in your own little reference sheet here. But this is from the previous video when we talked about these, and we have all these formulas and some definite in the hyperbolic functions, there's some definite connections back to and some similarities with the trig functions and the connections that the trig functions have amongst each other, like the relationship between sine of x and cosine of x, and the relationship between their derivatives and the identities that connect them. In a similar way, sinh, hyperbolic sine, and cosh, hyperbolic cosine, have some similar relationships, not exactly the same because they're related through the unit hyperbola, not the unit circle, but some similar identities and similar connections. And so you can kind of lean into what you know about your trig functions to help you remember and memorize what you are now going to have to know about your hyperbolics. Okay, all right, so practice those derivatives.